Welcome to the course on an introduction to information theory. In today's lecture, we are going to first talk about joint typical sequence. Now, to prove Shannon's noisy channel coding theorem, we are going to make use of typical set decoding, and to explain typical set decoding, we first need to explain what do we mean by a joint typical sequence and what are the properties of joint typical sequence. So, this lecture is about joint typical sequence and its properties, which are known as joint asymptotic equipartition property. So, a set of jointly typical sequence of this pair xn and yn with respect to this joint distribution P of xy is a set of n sequences whose empirical entropies is epsilon close to the true entropy. So, the joint typical set is defined as follows. So, it is a pair of random variables xn and yn, xn belonging to xn and yn belonging to yn, which satisfies these properties. So, this is the true entropy of x and this is the empirical entropy of x, and what we are saying is the absolute difference of this is less than epsilon, and that is what we meant when he said the set of typical jointly typical sequence with respect to joint distribution of P of x and y is the set of n sequences whose empirical entropies is close to the true entropies. Similarly, this is the true entropy of y and this is the empirical entropy of y. This is the true joint entropy of x and y, and this is the empirical entropy of the joint distribution P of xn and yn. Now, note that for x and y to be jointly typical, we need all these three conditions to be satisfied. So, if x and y is a n bit sequence and it is a jointly typical sequence, then it will satisfy these three properties. Okay. Now, equivalently, we can also write that if x and yn are they belong to the jointly typical set, then these three relations hold, and this comes directly from the conditions that we have written here. So, you can see from this condition, so 1 by n minus log of P of xn when this is greater than true entropy h of x, then this has to be less than epsilon. So, from here we can write 1 minus n log of P of xn to be less than h of x plus epsilon, and minus of log P of xn is less than n times h of x plus epsilon, and if we multiply both sides by minus 1, we get log of P of xn to be greater than minus n of h of x plus epsilon, or P of xn is greater than 2 raised to power minus n h of x plus epsilon. And this is what I have written that P of xn is greater than 2 raised to power minus n h of x plus epsilon. Similarly, we can see from this condition we will get this one, and from this condition following the same procedure we will get this condition. Similarly, we can prove that P of xn is less than equal to 2 raised to minus n h of x minus epsilon, and we can also prove this as well as this. So let us go back and look at this. So if you have, let us say this is my A and this is B. Now if B is greater than A, then I will write this as B minus A is less than equal to epsilon. So h of x minus of minus 1 by n log of P of xn, that has to be less than equal to epsilon. So this becomes h of x plus 1 by n log of P of xn. This is less than equal to epsilon, or I can write 1 by n log of P of xn to be less than equal to epsilon minus h of x, or log of P of xn can be written as less than equal to minus of n h of x minus epsilon, or P of xn is less than equal to 2 raised to power minus n h of x minus epsilon. So this condition can be written equivalently like this. Okay, so we just now showed that P of xn is less than equal to this. Similarly, we can show that P of yn is less than equal to this, and joint probability of x and y, this is less than equal to this. So these will follow from this condition and this condition. So in other words, this follows from the definition of joint typical set. So if xn and yn, they belong to this joint typical set, then we know these conditions should be satisfied. Now let us prove some properties of these joint typical sequences. So if x n y n are sequences of length n and they are drawn independent identically distributed according to this distribution, then these following conditions hold. What's the first property? Probability that xn and yn belongs to joint typical set, that probability approaches 1 when these length of the sequence is very large. So probability that xn and yn are jointly typical, that probability goes to 1 as n increases, as n is very large. And how many such jointly typical sequences are there? That is basically upper bounded by 2 raised power n joint entropy of x and y plus epsilon. So, it is roughly 2 raised power n h of x y. These many numbers of jointly typical sequences are there. And what is the third property? If xn tilde and yn tilde, these are independent end length sequences with same marginals given by this, then probability that xn tilde and yn tilde, they belong to this jointly typical set, this probability is upper bounded by this 2 raised to the power minus n, mutual information between x and y minus 3 epsilon. Or you can also show that probability if xn tilde and yn tilde are independently drawn, then probability that they are jointly typical, that is upper bounded by this probability. So we are going to prove one by one each of these properties of jointly typical sequence. So we know from law of large numbers that minus 1 by n log of pxn, that converges to entropy, and this converges is in probability. This can be shown easily. So this is 1 minus 1 by n log of p of xn. Since p of xn, this is IID distributed, so I can write it as is equal to minus 1 by n log of p of, let's say, x1, p of x2, like that, p of xn. Now this can be written as minus 1 by n. So this is log of products, that can be written as sum of log terms. So this can be written as summation log of pxi, where I is 1 to n. I can write it like this, and this is expected value of log of p of x, and this converges is in probability. This follows from the weak law of large numbers. Equivalently, I can write the same condition like this. So probability that expected value of minus log of px, and the absolute difference between that and the true entropy, that is absolute difference greater than epsilon, is less than some small epsilon. Let's say call it epsilon dash 1 or something like that, okay, which we are choosing as epsilon by 3. So this is equivalent to this statement, that minus 1 by n log of p of xn converges to entropy, and this convergence is in probability. So this is an alternate way of writing the same thing. Similarly, we can write that minus 1 by n log of yn, it converges to entropy of y, and this convergence is in probability, and the joint distribution of xn and yn, that also converges to this joint entropy of x and y in probability. And as we said, we can equivalently write these conditions as follows, that there exist, let's say, some n2 and n3, such that for all n greater than n2, probability that the absolute difference between the empirical entropy and the true entropy exceeding epsilon is less than some small epsilon, we are calling it epsilon by 3, and similarly probability that the absolute difference between the true joint entropy and the empirical joint entropy exceeding epsilon is less than some epsilon by 3, and this holds for all n greater than equal to n3. So then we can combine these three conditions. One is this one, another is this one, and the third one is this one. So if we combine these three conditions, what we get is the probability of this set of jointly typical set, this probability is greater than 1 minus epsilon for all n which is greater than the maximum value of n1, n2, n3, right. As we know that from the property of joint typical set, we know that these three conditions has to be satisfied. right? These three conditions have to satisfy if Xn, Yn belongs to a jointly typical set. So what we have shown right now is that probability that Xn, Yn belongs to the joint typical set, which is satisfying these three conditions, that happens for n greater than maximum of n1, n2, n3, and we have shown that if we add all of these, we get the probability of typical set to be greater than 1 minus epsilon, because probability of this is less than epsilon by 3, probability of this is less than epsilon by 3, and this probability is also less than epsilon by 3. So if we add this probability, we get overall probability less than epsilon. So in other words, probability that it belongs to the typical set is then 1 minus epsilon, which is the complement of this probability. Okay. So we have proved the first property, that if n is large, Xn and Yn probability that they belong to joint typical set, that probability is 1 minus epsilon, and epsilon is a small quantity. So this probability goes to 1 as n increases. Next property is regarding the size of the jointly typical set. So how large is the size of the jointly typical set? So to prove this, we know that joint distribution of x and yn, sum over all x and y, that probability should be 1. Now if we sum them over only jointly typical set, so you can think of it, this summation is over one set where xn and yn, they are jointly typical, which is this, and then there is a set which is a complement of this, right, complement of this jointly typical set. So if I sum it over only jointly typical set, I get this sign that this summation should be less than equal to 1, and invoking this property, which follows from the definition of jointly typical sequence, I know from here P of xn yn, this is less than equal to this, and greater than equal to this quantity. Okay. So using this relation, if we plug in the value of P of x and yn here, we know that this is greater than equal to 2 raised to the power minus n h of xy plus epsilon, right? And so we are replacing this by a smaller quantity, so that's why we again get greater than equal to, and so number of elements in this jointly typical set multiplied by lower bound on this joint probability. So this has to be less than equal to 1, and from here then we get the condition that this number of elements in this jointly typical set is less than equal to 2 raised to the power n times joint entropy of x and y plus epsilon. Next, we have shown that as n goes to infinity, or n is large, we have shown probability that xn and yn are jointly typical, that probability is greater than equal to 1 minus epsilon. So then we can write that 1 minus epsilon is less than equal to this probability. Why? Because when n is large, probability that xn and yn are jointly typical, that probability is greater than 1 minus epsilon. So when we are summing this over this jointly typical set, this summation is greater than 1 minus epsilon. And we know that this is upper bounded by 2 raised to the power minus n h of xy minus epsilon. This follows from the properties of jointly typical set. So if we upper bound this by this quantity and we plug this in here, we get this less than equal to sign here. So what we get is 1 minus epsilon is less than equal to number of elements in this jointly typical set multiplied by this. And from here we can get a lower bound on number of elements in this jointly typical set, which is basically greater than or equal to 1 minus epsilon 2 raised to the power n times joint entropy of x and y minus epsilon. And when epsilon is very small, this is roughly, you can see there are roughly 2 raised to the power n h of x y elements in this jointly typical set. The third property that we are going to prove is as follows. So xn tilde and yn tilde are independent and they have the same marginals as x of n and y of n. Now we want to find out, if we independently take xn and yn, what's the probability that they belong to the jointly typical set. Now this probability can be evaluated since xn tilde and yn tilde are independent. So we can write this summation of p of xn yn sum over this jointly typical set. We can write this as product of these, right, and we are summing up over this jointly typical set. Now we know that p of xn is upper bounded by 2 raised to the power minus n h of x minus epsilon. We know that p of yn is less than equal to 2 raised to the power minus n h of y minus epsilon. Again, these follows from the properties of the jointly typical set, and we know that number of elements in here is upper bounded by 2 raised to the power minus h of xy plus epsilon, right. So if we plug in these values of p of xn, p of yn here, right, and sum over all xn, yn belonging to this jointly typical set, which is number of such elements is upper bounded by this. If we do that, what we get is this term, which we are getting from upper bound on number of elements in this jointly typical set, this term which we get by upper bounding on probability of xn, and this we are getting on p of yn, upper bound on this. So we combine all of this, what we are getting is 2 raised to the power minus n h of x plus h of y minus h of xy, okay, and we get minus 3 epsilon. Now this particular term h of x plus h of y minus h of xy, this is nothing but mutual information between x and y. So we plug that in here, we get this third property which says probability that if xn and yn tilde are independent and have same marginals as x of n and y of n, then probability that they are jointly typical is less than 2 raised to the power minus n times mutual information between x and y minus 3 epsilon. We can similarly also get a lower bound on the probability that xn tilde and yn tilde belongs to a jointly typical set. And how do we get this? So again we start with summation of p of x and yn over this typical set. Now we are going to lower bound these probabilities. So this is lower bounded, p of xn is lower bounded by this, and p of yn is lower bounded by this. And similarly, number of elements in this jointly typical set, that is lower bounded by this quantity. So if we plug in these values, what we get is probability that xn tilde and yn tilde, which are independent, are jointly typical is given by is lower bounded by this probability. Now, so what we have seen so far is, so we have total these many numbers of typical x sequences and these many numbers of typical y sequences. However, they are only 2 raised power n times joint entropy of x and y number of jointly typical sequences. So if we pick up independently, let us say a typical sequence from x and typical sequence y, they will not be jointly typical. So not all pairs of typical x, n and yn sequences are jointly typical, because we only have so many numbers of jointly typical sequence. In fact, this probability is given by this divided by this into this, which comes out to be this. So probability of any randomly paired chosen pair of xn and yn which are typical, probability that they are jointly typical, this probability is given by this. Okay. So in other words, what we can say is, we can consider around 2 raised to the power n times mutual information of x and y. We are going to encounter those many number of pairs before we are likely to get one jointly typical pair. So as I said, because the probability of a randomly chosen pair being jointly typical is this, so we can roughly encounter so many such pairs before we are likely to encounter a jointly typical pair. So in other words, we can conclude that we have total of 2 raised to the power n times mutual information of x and y, those by number of distinguishable signals. So what we have done so far is, we have described what is jointly typical sequence, and we have described some of the properties of jointly typical sequence, namely what is the probability of occurrence of jointly typical sequence, how many such jointly typical sequence exist, and if we randomly pick 2 typical sequence, what is the probability that jointly they are also typical, that we have shown. Now these properties we are going to use to prove our noisy channel coding theorem, which we will talk about in the next lecture. Thank you.